All right, we're going to start looking at that last category of ways to approach limits, which is algebraically. This is going to be most of the problems that you do in this course. You will be approaching them algebraically. Certainly, you will do things numerically and graphically as well, but this is where the rubber really hits the road, and you got to make sure that your skills are honed to be able to solve these problems. So we're going to approach this by actually just starting with an example. We're going to look at the limit as x approaches 4 of the function that is x squared minus 16 divided by x minus 4. So for all of these, I'm going to try to be consistent here. I want you to make step 1 always be to try direct substitution. You should be able to see this function already is going to have an issue, but let's just verify what happens when we try direct substitution. If we try to take 4 and plug it in for x, we're going to end up with 4 squared, which is 16 minus 16 divided by 4 minus 4, which is equal to 0 divided by 0, which I've already mentioned in another video, is something called indeterminate form. I know nothing about my answer when I get 0 divided by 0. I cannot determine what's going on. It could be that the answer is 0. It could be that the answer is infinity. It could be that it doesn't exist. It could be that it's a number like 4 or 10. I cannot determine what is happening, so direct substitution does not work at this point. Step 2, if we can't use direct substitution, is going to be to algebraically modify things. So looking at this problem, x squared minus 16, I notice is a quadratic. And as soon as I see that this thing is a quadratic with this exponent of 2, I should automatically be thinking about things that I can do to a quadratic. And one of the things that you should feel really comfortable with is factoring. So this does, in fact, factor out. X squared minus 16 can be factored. Now, at this point, this is the time that I'm going to make this point, and this is a big deal. What I see people do when they go from this first line to this second line is this. They'll show the work algebraically for the function, but they will leave off the limit notation. It is not okay to just roll with this. This is not a limit problem, but we are being asked to evaluate a limit problem. So I'm just emphasizing the point that I want you to keep the limit notation in front of the function. Do not just ignore it and scrap it. You've got to keep it there. So what's cool about this now is x minus 4 and x minus 4 will cancel out, so this becomes a much simpler problem. So now just algebraically looking at this, we can ask ourselves, is this function continuous at 4? And the answer is clearly yes. If we go back to step 1 now and try direct substitution again, I can take this value of 4, plug it in for x, and my answer here will be 4 plus 4, which is 8. So we need to approach these two functions and ask ourselves, are these the same or are these not the same? That is the question of the hour. Are these two functions, x squared minus 16 over x minus 4 and x plus 4, the same? Algebraically, we've shown that they are equivalent. I can reduce the more complex version to get x plus 4, and they are algebraically equivalent. However, graphically, there is one small difference. If you graph x plus 4, you're going to get a line. It has a slope of 1. It's going through the y-intercept of 4. If you were to graph x squared minus 16 over x minus 4, you are going to get a line. It's going to have a y-intercept of 4, and it's going to have a slope of 1. But there is one difference. There's one big difference in the graph of this versus the graph of this. And hopefully you're seeing it. The difference is that this function that has a denominator has a gap or a hole, or in other words, a removable discontinuity that we have removed at the value x equals 4. So if I were to graph x squared minus 16 over x minus 4, I would do so by identifying a gap or a hole at the value when x is equal to 4. So the question is, why am I able to say that the limit is equal to 8? And the answer has to do with the fact that, again, when we find a limit, we don't care about what's going on at that point. What we care about is what happens as we get infinitely close from both sides. And so that is why I can algebraically say that this thing and this thing, for this purpose of evaluating the limit, are going to give me the same answer, because I don't care about the actual value of what's happening at 4. I care about what's happening as we get infinitely close to 4, and we can do that approximation by algebraically simplifying this thing and using direct substitution. So I've said a lot of words. Let's recap. Here's what we did. We looked at this thing, we plugged 4 in, and we got 0 divided by 0, which is indeterminate. So then we factored the top, we crossed those out, we got x plus 4, we plugged 4 in, and we got an answer of 8. All right, let's look at another example. We're going to find the limit of this function x squared minus 4x plus 3 all over x squared plus x minus 12 as x approaches 3. So again, step 1, same step 1, we're going to try to figure out what happens when we plug 3 in for x. We're going to attempt direct substitution and see what happens. I've plugged 3 everywhere in for x. And I get 0 divided by 0. Again, indeterminate form. I cannot determine what is going on. So I am stuck. Only not really. We go to step 2 and we see if we can algebraically manipulate this thing to change it so that we can find out what the answer is. So I start by rewriting my limit notation. Do not drop the limit notation. I've noticed that I have a quadratic on the top and a quadratic on the bottom. Let's see if we can factor these two things. I'm looking for two numbers on the numerator that will multiply to 3, that will add together to -4, and there are such numbers. -3 times -1 is +3, and those numbers add together to -4. And now let's take a look at the denominator, two numbers that multiply to -12 that add together to +1. So we get x plus 4 and x minus 3. And this is super great because check this out. X minus 3 and x minus 3 will cancel each other out. And that, if you'll notice, is where we had the issue when we plugged 3 in initially with direct substitution. We have just eliminated the spot where we had a problem. In other words, we've eliminated our discontinuity. The function is no longer discontinuous, it is continuous, so with the remaining portion of my function, I can use direct substitution. So here we go. We can take 3, and when we plug it in for these values of x, we no longer have any issues, and our answer is 2/7. So what we're saying is that if I were to graph this function and look at what's happening as x gets infinitely close to 3 from both directions, I'm approaching 2/7 as a y value or as a height, as a vertical distance.